Okay, any questions before we continue? Well, you see, you cannot just rotate this, chain this back. If you want to go to a different reference frame, still the angular velocity vector will make an angle theta with this line. You cannot change the direction of the angular velocity vector by just changing your reference frame or changing your coordinate axis. There will still be a component of the angular momentum that is not a long momentum. But of course, if you are rotating it just like this will be a different motion than this one though. If this is the motion, then the angular momentum will be in the upward direction, just like the angular velocity. So you won't get this problem. But in this problem, what happens is this line connecting these two masses makes an angle theta, which is not 90 degrees, which is not 0, with the angular velocity. In this case, the angular momentum will not be in the direction of omega. So we already had kind of discussed that the torque is nothing but dl by dt of my system. So you see, in this example, as my object is rotating, the angular momentum was in this direction, so it's rotating. So the angular momentum is constantly changing in this one. There's a constant change of angular momentum. But that tells me that there should be some torque acting on my system. So if you want to just rotate it like this, you cannot just you cannot just start it rotating and then set it free. It will not continue rotating like this. What will happen is if you just give it an initial spin, if we were in empty space and we would just start them rotating just like this and release them, what would happen is that it will just flatten out and it will start rotating in this orientation. Or rather in this orientation. But to keep them doing this motion, we have to exert some torque on the system. Now, for those who have a car or who is familiar with if your family has a car, so somebody should take them to a repair shop every now and then to fix the rod and the balance. Now, what is actually happening is that if you just look at the wheel that has been adjusted for the balance, they just attach some masses on the rim. It is basically this is what they call an imbalance in the wheel. Is basically the mass distribution becomes non-symmetrical. If the mass distribution is non-symmetrical, in that case the angular momentum is not in the direction of the angular velocity. The angular velocity is always in the direction of the axis as your wheel is rotating. This is the direction of the angular velocity. It is fixed. If angular momentum is not in the same direction, then the axis of the wheels should exert some torque on the wheel to keep it rotate, to change the angular momentum. But this torque means that there is a force that the axis exerts on the wheel and hence the wheel exerts a force on the axe, which will just cause the axe to get old earlier. So you will have to change the axe sooner, unless you make these adjustments. So this is basically what they do in that rot and balance adjustment in the cars. They make sure that the angular momentum is in the direction of the axe of the wheels. Now, any questions? Now we can just use some applications of this angular momentum concept. But before that, let's just see that this is also conserved, the angular momentum. Let's just imagine we have a system of particles . We have a system of particles. They're just moving around. They might be exerting some forces on each other. So each one will feel some force, let's say Fi. Fi will be, some of it will be some external force, plus some of it will be due to the jth particle. This is the internal force acting on my object. It can be a rigid object or even a non-rigid object. We can still talk about the total angular momentum of the system. It will be mi/ri cross pi. We can talk about the rate of change of the angular momentum of the system, which will be there's no mi, sorry. Ri cross Fi external plus Ri cross Fij, the internal. This is nothing but the total external torque acting on my system. So I have some bunch of forces acting at the point Ri. Each one will be creating some torque. So the rate of change of the angular momentum of my system will be equal to the external torque. Now the internal torque, this is the internal torque for this system. I just choose some coordinate axis somewhere. This is Ri for this object. This is the external torque. There's nothing to do with that. Now this is what we call the internal torque. Now it's not so trivial to see that the internal torque will cancel in every case. But especially in two particular cases, let's just imagine this one. Just take two of the objects. This exerts a force. This is 1, this is 2. This is the force acting on 1 due to 2. This will be the force acting on 2 due to 1. And we know that F12 is equal to minus F21. This is Newton's third law. Now, if this is satisfied, let's see. This is R1. This is my R2. What is the direction of R1? Torque 1. This is the z-axis, xy. This is equal to R1 cross F12. This is equal to, well, in fact, let's do it in a different way. Let me calculate directly torque 1 plus torque 2. This is equal to R1 cross F12 plus R2 cross F21 which will be equal to R1 cross F12 minus R2 cross F12. Now I use Newton's third law. This is equal to R1 minus R2 cross F12. But R1 minus R2 is nothing but this vector over here. This orange one. So R1 minus R2 is in the direction of F12. They are both parallel to each other, so if we have parallel forces, then their cross product is 0. Because mainly either their angle is 0 or the angle between them is 180 degrees. So at least in this case, when we have these two objects exerting forces directed towards each other, in such a case, the internal torque just cancels. So the rate of change of the total angular momentum of a given system is exactly equal to the external torque acting on my system. Just like the case of the total momentum, linear momentum of the system, we had seen that the rate of change of the total linear momentum of a system is equal to the total force, external force acting on the system, and it doesn't depend on the internal forces. Just like that one, the rate of change of the angular momentum of the system is also equal to the rate of change is also equal to the total torque created by the external forces acting on the system. It doesn't depend on the internal forces acting on the system. Then of course you can claim that what if these forces are not just pointing towards each other? What if they exert forces in some other direction? Well, we don't have such cases until we study magnetism. But until we study magnetism or similar forces, all the forces we know, they're just pointing along the line connecting the two objects. And hence the rate of change of the angular momentum, will be determined only by the external torque. And if there is no external torque acting on my system, then the rate of change of the angular momentum will be 0. So we have a conserved quantity. So this is in fact the reason why we had seen in the yo-yo example, we had seen this conserved quantity. If we go back to that conserved quantity, this was the conserved quantity in the example of the yo-yo. M times V center of mass, this is the momentum of the center of mass. R times the linear momentum of the center of mass, this is nothing but R cross P. The angular momentum due to the translational motion of the center of mass, plus this is nothing but the angular momentum due to rotations around the center of mass. So this is nothing but the total angular momentum of the yo-yo, which was conserved. Now let's do some examples. No, sorry, that wasn't the example of the yo-yo, that was the rolling ball. Again, we have the rolling ball. It will be rolling towards the right. So its angular velocity, the direction of the angular velocity is into the screen. So let's say that at a given instant, it is moving with some velocity v, the center of mass. Its height is r. So what is the angular momentum of this object? And at this instant, it is rotating with angular velocity omega. At least Lz. This is the z-axis. Now the reason why I'm asking for Lz is this is the angular momentum in the direction of omega. So if we have rotations, we have omega. So the angular momentum due to that rotation, the component along omega will be always I times omega. So that's why I'm looking at the z component only. So what is the angular momentum of this object? I have this ball at a given instant. It is center of mass is moving with the velocity v center of mass, and it has an angular velocity omega. I don't know if it is rolling without slipping or not, but these are the given information. So how can we write the angular momentum? I also want to write an conserved angular momentum. So let me first clarify what we mean by conserved angular momentum. Remember, the rate of change of angular momentum is given by the torque. Angular momentum we defined as r cross p for a point object, and the torque for a single force it was r cross f. Now, if somebody asks you what is the angular momentum of this object, or what is the torque acting on the object, the first question you should ask is relative to which point? Because we first have to choose some r. So we have to, without specifying this r, or without specifying an origin, we cannot talk about the torque, we cannot talk about the angular momentum, because if we change our origin, we will change the torque. And we will change the angular momentum. So let's see, what is the angular momentum relative to point A? Remember, whatever origin you choose also, we had already shown that the angular momentum can be divided into two parts. The angular momentum due to the motion of the center of mass plus the angular momentum due to rotations around the center of mass. So relative to this point A, what can you say about the angular momentum?
Center of mass times omega.
Or let's say the z component. Well, let's just write it down. This is our expression. This is my reference point. So the position of the center of mass is in that direction. It's in this direction. This is the position of the center of mass relative to the point A. My center of mass has linear momentum in that direction also. So the angle between these two vectors, r and p, is 0. Which just tells me that our center of mass cross p center of mass is just 0. So I don't get any contribution from the first term. This is 0. Plus, and of course I have this contribution, my object is rotating around the center of mass. I center of mass omega, plus or minus. I'm looking at the z component in the minus direction, times minus 1. Now, is this angular momentum conserved? Okay, now I wrote one angular momentum for one choice of this reference point. Is this angular momentum conserved? Why or why not? Should be or not? You see, first of all, we already have discussed that omega is changing in time. So it is definitely not conserved. This is constant, omega is changing in time, so this product is changing in time. So this is not conserved. Which means if an angular momentum is not conserved, it basically means that there is some external torque acting on my system. Is there an external torque acting on my system? In this one. So what are the forces acting on my system? There is a normal force acting on my system. There is the weight acting on my system. There is also the friction, let's say in this direction. Well, the normal force and the weight, they will create the same. Well, let's write the torque relative to the point A. What is the torque? Well, I have these three forces, so I have to sum all the torques created by these three forces. Now, what is the torque created by the weight of the object? Relative to the point A. Remember, this is my point A. I'm writing the torque relative to this point. Well, this is the definition of the torque. Let's just say this distance is d. Let's just give it a name. So the torque due to the weight will be d times the weight is mg times, let's just say this angle is theta. So this is the direction of the weight. So this is my d vector. This is the d vector. This is the d vector is this one. Sorry. This is the normal force. Sorry. D times the normal force. This is D. This is the normal force. The angle is just pi 90 plus theta. Sine of 90 plus. This is the normal force. This is the angle. So this angle over here is theta. This is the normal force. This is the angle between D and theta is just pi over 2 plus theta. So we have the sine of pi over 2 plus theta. It will be cosine theta. This is is this correct? Do you agree with this one? I have, this is D in this direction. This is the normal force. So I define this angle as theta. This is the normal force. This is D. So this is pi over 2 plus theta. So for the cross product D and in which direction? D and D cross N. So it's in the minus Z direction. Now let's see. This is D, this is N. Take your right hand. It's in the plus Z direction. Now let's continue. The weight. The torque created by the weight, the torque is acting right over here. The weight is acting over here. So its distance is this one. So it is d cosine theta. This is the distance at which the weight is acting right over here, d cosine theta. The weight has magnitude mg. the angle between this vector plus the weight is 90 degrees, sine of 90 is just 1. What is the direction of the torque created by the weight? Minus z. Now finally we have the friction force. Friction force is also acting like this way, so we have this D times F friction. Now if we move the friction force over to this point, this is our vector D. This is the friction force. So the angle between the two is theta, sine theta. What is the direction? It's plus z. Now we had already, by just writing a Newton's law, we know that this is only accelerating in the horizontal direction. There is no vertical acceleration. There shouldn't be any vertical force. So it tells me that n is equal to mg. Well, sine of pi over 2 plus theta is equal to cosine theta. So these two terms have the same magnitude, one in the plus z, the other one in the minus z direction. So they will cancel each other. But still we have one more term left. So the torque with respect to this reference point A is non-zero. There is an external torque acting on my system if I calculate the torque relative to the point A. So the angular momentum is not conserved. It will be changing in time. So is there a point that I could have chosen relative to which the torque would have been zero? Well, this is our system. I have here, there is the friction force, there is the normal force, there is the weight. Yes? What? Well, in fact, any point on the ground, if you just take any point on the ground, let's say this point, B, torque relative to the point B would have been zero. Now, the torque created by the normal force and the weight, they always cancel each other. They will always cancel each other because they are passing through the same point. They are along the same line. But if we choose the point B to be on the ground, torque relative to the point B is only due to the friction force, if any, but the torque due to the friction force is always zero. I don't care. You see, our definition of the conservation of the torque is independent of whether we have angular acceleration or not. As long as there is no external angular velocity, external torque, angular momentum will be conserved. Now let's come to your point. What is the angular momentum of this object? Again, let me write the expression. Since it might be slipping, it's not easy to identify an axis which is instantaneously at rest, so we cannot use such an axis. But we can still use this expression. Now this object is moving towards the right. So what is the angular momentum of this object due to this term? Well, let's say this vector. Let's define that as, this is our center of mass. And the sphere has some radius on it. So let's calculate this term. Lz is equal to. Now this is my arc. My object is moving in this direction. If r is some, okay, this is r. My object is moving in this direction. This is the angle between the two. R cross P is into the screen. So it is our center of mass times m times v center of mass. Let me just call this angle theta times sine of pi minus theta. It's in the minus z direction. This is the angular momentum due to the translational motion of the axis passing through the center of mass. What was its rotation axis? Okay, omega is into the screen. So what is now this term? Omega is in the minus z direction also. So if we just add it plus I center of mass times minus omega in the z direction, or omega in the minus z direction. So this is the total angular momentum of my system. Oh, sorry. Since we are already looking at the z component, I don't have these. So Lz, well, sine of pi minus theta is sine theta. Minus mv center of mass, r center of mass times sine theta, minus I center of mass times omega. This is the z component of the angular momentum. Now let's see. This is my r center of mass. This is the angle theta. So r center of mass times sine of that angle is nothing but the radius of my sphere. Minus mv center of mass times r plus I center of mass times omega. This is with respect to the point B. Of course, it has angular acceleration. Omega is changing in time. But due to friction, V center of mass is also changing in time. If there is no friction, well, V center of mass doesn't change in time, omega doesn't change in time. So whether there is friction or not, this combination is always conserved. In fact, that is what we had already seen in the rolling example. So if, for example, we wanted to determine what will be the angular velocity of the object, we have an initial angular velocity, initially zero, translational velocity, let's say. In that case, initially this would be zero, this would have some initial value. After some time it will start rolling without slipping. If it is rolling without slipping, then the center of mass is nothing but omega r. So we know the, well, let's write it down. Example. Omega initial is equal to, let's say, omega 0. V center of mass initial, this is 0. Now, after some time it will start rolling without slipping. So omega final will be, let's say, omega 1, and V final will be omega 1 times r. This is the condition of rolling without slipping. So we can ask the question, what is omega 1? What is the angular velocity of the object when it starts rolling without slipping? So we just use the conservation of this quantity. So initially, it is just I center of mass times omega I. Finally, it is I center of mass times omega 1 plus mr omega 1 times mr squared omega 1. This omega I is 0. Omega 0. So this tells me just in one line what is the angular velocity when the object starts rolling without slipping. By the way, just have a look over here. Now again, does this ring any bells? I center of mass plus mr squared. It is nothing but the moment of inertia for rotations around this instantaneously fixed axis. Because once you see, the expression over here is the total angular momentum that we have. We can write it in whichever form you want, as long as you get the correct, right? You are calculating the correct thing. It should give you the angular momentum of the object relative to the point B. Now here, up to now, we always divided into two, the angular momentum due to the translational motion of the axis passing through the center of mass plus rotations around this axis. But once it starts rolling without slipping, we also have a fixed axis, instantaneously fixed axis. So the angular momentum, we can forget about this splitting between the translational motion of the axis, which is 0, and the rotation around that axis. This is the angular momentum of rotation, angular momentum of an object rotating around the fixed axis. And this is the moment of inertia around that axis. So again, we are back to the parallel axis theorem. If the parallel axis theorem didn't hold, then here we wouldn't have a consistent description of the system. Now, any questions? Oh, this one. No, I mean, let's leave it for, first, if you have any questions about this rolling without slipping example and the conservation of angular momentum. Now, the crucial thing in this example was first to determine a reference point with which you will be writing down the angular momentum so that the torque would be 0. We tried 2 points. The point A, if we calculate the net torque with respect to this point A, in that case the torque is non-zero and hence angular momentum is not conserved. You cannot use the conservation of angular momentum. Then we said that if we write the torque relative to this point B, in that case we had seen that there is 0 torque acting on my system, so angular momentum is conserved. And hence we can use the conservation of angular momentum written relative to this point B. Then you can just use conservation law and obtain whatever result you are looking for. Yes, now back to your question. No, I am calculating the angular momentum relative to this point. In fact, if you calculate it relative to any point, as long as you are in an inertial reference frame, you fix your inertial reference frame, this will be the total angular momentum of the system. No, this is the direction of the angular velocity. It is rotating like this. The angular velocity is fixed. This is the direction of the angular velocity. Okay, we can discuss after the lecture if you want. Just one more example. If you can survive for 5 more minutes. Well, this is an old example that we discussed. Remember we had this table, there was a hole in the middle of the table and we attached the mass. Okay, we had this table. There was a hole over here, there was a string going down, which we were exerting a force on the string, and there was an object doing circular motion. Let's say at this, let's say this is the radius r. It had some speed v. We were trying to calculate kind of the work, etc., but at some point we were kind of stuck. What is this force? I mean, if you remember, we were pulling it down. Now, when the radius of this circle just changes, becomes some other value, what should be the force? Now, we said that if the radius is constant, we already know that the force has to be equal to mv squared over r. So if we change the radius, how does the velocity change? Well, there's no energy conservation because we are exerting a force on our mass, so that force will be doing some work on the mass, so the kinetic energy will be changing. There's no potential energy anyway, so we cannot use the conservation of energy. Well, there are external forces acting on my mass, so there are no momentum conservation, so we cannot use momentum conservation. Can we use conservation of angular momentum? Relative to which point? You see, if you want to talk about the angular momentum and the torque, you have to talk about relative to which point. If you consider this center A, the torque relative to the center A, there is a single force acting on my mass M, and that force goes through the point A. So the torque relative to the point A is 0, which tells me that the angular momentum relative to the point A is conserved. So what is the angular momentum relative to A? So this is the picture we have now. If we just look at it from the top, this is my mass, this is the point A, so it is attached by a string to the point A. It is moving speed v. Now the angular momentum relative to the point A, let's say this is the z-axis pointing out. It's always r cross p. It is r times m times v. The angle between the two is 90 degrees. And its direction plus that. So this just tells me that v times r is equal to constant. If you pull the string down, the string will get smaller. The radius of the circular orbit will get smaller and smaller. As r gets smaller, its speed should increase. And this is in fact how it increases as a function of r. So v will be equal to v0, r0, whatever the initial values were, divided by r. Now this is in fact similar to if you have ever seen a skier. He or she will start rotating with the hands open, and when she closes her hands, she will start to spin much faster. The reason is mainly angular momentum should be conserved. Angular momentum is basically I times omega. In this example, I times omega is nothing but mvr. the case of this skier, since he is pulling in the masses, you see the moment of inertia is mass times r squared. So if you reduce the distance from the rotation axis, I gets smaller. If I get smaller and angular momentum is conserved, the angular velocity should increase. So the skier, when he or she closes his or her arms, she starts rotating with a larger angular velocity, just as in this example, if you just pull the string, causing the mass to rotate a smaller circle, as r gets smaller, its speed will increase. And hence, from this expression, you can determine how the force changes, how the force that you should exert on the string should change as you pull it down. So this you can also write as mvr squared divided by r to the 4. Now the reason why I wrote it as Vr squared is I know that this Vr is constant. Vr is just constant during the motion. As the radius gets smaller, if you just reduce the radius by a factor of 2, you have to increase the force that you exert by a factor of 16. This is just another application of the conservation of angular momentum. Correct. So it should be, if you reduce the radius by a factor of 2, the force you should exert should increase by a factor of 8. You can do it slowly, you can do it faster, but nevertheless, when the radius gets twice as short, the force that you exert should get 8 times larger. Now, any questions? Now, on Thursday, we will study one more example. So you can just start thinking about it from now. Let's say you have a rod, and then there is a ball of mass m. This has a mass m, length l. So the ball comes with a velocity v. There is no friction. It hits and it sticks to your rod at the end, and everything starts rotating. What will be omega? What is the velocity of the center of mass? They stick together, and after that they get moved together. Now, with the knowledge of the angular conservation of angular velocity, although it looks quite complicated, it will be quite easy to solve this problem. That is for Thursday. Okay, see you on Thursday.